We can hear you.
Okay, good.
Recording in progress.
So my name is Olga Kucherovskaya. I'm from Texas A&M University, and I'm chairing this plenary session. And today we have two very distinguished speakers, and it's my real pleasure to introduce them to you. And I did some homework, and let me share my slides with you. So, can you see my slides?
Yes.
Okay. So the first speaker in our session is Professor Peter Serov from Ludwig Maximilian University of Munich. He received his master and PhD from the University of Heidelberg. Then for the next couple of years, he stayed as a scientist at this university. And for the next 2 years, he was at Michigan State University. And in 1996, he joined Ludwig Maximilian University, and all his further career was connected to this university, where currently he is professor of experimental physics. His research interests are very broad. They are ranging from laser ion acceleration to fundamental physics biostandard model, from medical physics to applications of medical physics to nuclear spectroscopy and nuclear photonics. But he is the best known probably for pioneering and seminal work on thorium nuclear clock, where he is really the world leader. And it is witnessed by the set of these Nature papers, where all the milestones in this field were developed by him and his group. And so we are very lucky to have him today with us, and he will share with us this research in thorium nuclear clock. Peter, the floor is yours. So let me stop sharing. Okay.
So you may see it now.
Yes.
Yeah, thank you, Olga, for this super kind introduction and announcement. And I'm very grateful to you and the organizers to give me, as a nuclear physicist, actually the chance to talk here in a laser physics workshop in this specific field, where we try to unite basically different fields from, that's what I also called, from the atomic to the nuclear clock. So we are trying to build a bridge from the nuclear physics to atomic physics to laser physics, finally approaching metrology, solid state physics, fundamental physics is involved. So it's a truly interdisciplinary topic that we are touching here, and I want to introduce that to you, starting from, well, giving a conceptual overview on how atomic clocks and thorium nuclear clock would compare, give applications of the nuclear clock as they have been proposed over the last 40 years, and show you what we learned actually on this elusive isomer. So it's an isomeric state, has a long lifetime, and what we learned about that from its first detection, from the first identification, which was not in the radiative channel, as we'll show you, but in an electron decay channel. Then we learned about, once you have it identified, you can start in characterizing it, and the characterization comprised the half-life, of course, but only, as I will show so far, in the neutral atomic state, while the ionic lifetime is still under investigation. We learned how to identify the hyperfine structure. We learned more to constrain the energy, the excitation energy. And there, now the last breakthrough was recently the first observation of a radiative decay, which for almost 50 years escaped observation. And I will show you what the perspectives are on ongoing and on planned activities, preparations for the ionic lifetime measurement, developing of suitable lasers, which we now, with the knowledge of the excitation energy, can develop for direct laser spectroscopy, and I will summarize in the end. So if we are interested in high precision frequency standards, I think it's worthwhile to take a look at the overall situation. about high precision clocks. And you see here this famous plot where it shows how from the start of the atomic clocks back in 1955, with the invention of the first atomic clock built by Essen and Perry, these on hyperfine splitting based clocks have gradually evolved and improved over time, leading then also to the redefinition of the second in 1967, which is still nowadays based on a hyperfine level. And then at some point, optical clocks appeared, and you see they are improving with a much steeper slope nowadays, even reaching down to the 10 to the minus 19 fractional uncertainty, of course, assisted by technological developments like the laser cooling frequency comb. So there is a whole lot of development going on, and we will certainly hear in the next talk after myself how this is being at the moment and anticipated to go on in the future. And you see what you have at the moment with the best atomic clocks, even now approaching into the 10 to the minus 19 range. There are limitations by field-induced, by thermal-induced perturbations, and a fundamental limit in the end would be the quantum projection noise that relates the interrogation time, the number of the interrogated particles, the number or the averaging time, and the line width of the clock transition. And the achievement at the moment is that two clocks adjacent to each other would lose only an accuracy in between each other of 1 second in more than the age of the universe in about 30 billion years, an amazingly and intriguing accuracy that has been reached so far. If you now compare and think, what is the situation for an atomic clock? Well, conceptually, it looks like a nuclear clock looks like an atomic clock. You have a two-level system that is driven by a stable laser in resonance, in a resonant loop here. You need a clockwork, for example, given by a frequency comb. And then you have a transition here for this two-level system coming from the atomic shell. So electronic excited states are used here. The energy scale is electron volts, as it is typically in atomic physics. If we now compare the nuclear system, it's basically the same. We also would like to use a two-level system here, but the problem in principle is that nuclear excitation energies are by far larger than in atomic systems. Usually they are hundreds of keV, MeV. So it's normally not conceivable that a nuclear transition would qualify as a transition for a clock. However, and now comes this very unique specific situation into the game of thorium-229, so a heavy isotope, it's in the actinide region, 2 protons below uranium. And there we have the very peculiar situation that we have the lowest excited nuclear state of all around 186,000 presently known nuclear excited states. And you see here on the right-hand side, the energy. So this is our best knowledge as of today. It's around 8.3 electron volts, which translates into a wavelength of around 148 nanometers. So it's in the vacuum ultraviolet. And the lifetime here, the half-life of this transition, this ground state decay, for example, is still not precisely known. It's of order minutes to hours. So it's about between 1,000 and 10,000 seconds. So the relative line width is intriguingly small. So this is the only candidate actually that we have in the whole landscape of nuclei that would qualify for a nuclear clock. And yeah, such a nuclear clock actually would be more than just timekeeping. You can even regard it as a quantum sensor, because the different operational principle compared to atomic clock, because it involves not only the Coulomb and the weak interaction, but also feels the strong interaction that contributes to the clock frequency. Moreover, the nucleus is small, the atom is large, the nuclear moments are accordingly small, so there is less sensitivity to perturbations by external fields, which gives an additional benefit to a nuclear clock. And there has been many papers in the literature over the years studying the sensitivity to new physics surges, which are promised to provide an enhanced the sensitivity by not small factors, but as you see, 4 or up to 6 orders of magnitude enhanced sensitivity to searches for new physics, as I will show in an example in a minute. So it's really an intriguing system that will give a unique opportunity to discoveries beyond the standard model, which cannot so easily or not at all even be accomplished with other technologies. Amongst them, of course, well-known topics that are also addressed in the atomic clock community. So the temporal variation of fundamental constants, which is an ingredient of many theories that unite the basic forces, and the temporal variation at the moment seen from an experimental perspective is still compatible with 0 on the level of 10 to the minus 18 per year. So minute changes need to be with a high precision over a long time be measured, unless you have an enhanced sensitivity that can be expected from the thorium isomer, according to, initially proposed by Victor Flambaum and his group, where measurements then would involve monitoring the ratio between a nuclear and an atomic clock over time, and even with a reduced precision of a nuclear clock, which is still not existing, but which will be hopefully soon come into existence, one could add an additional sensitivity factor to that to come into competitiveness on this level of precision that you need to measure or experimentally access at least the question of a temporal variation of fundamental constants. Moreover, it includes the test of the coupling of fundamental constants on the changing gravitational potential. You're testing the position invariance hypothesis, and by that, Einstein's equivalence principle, considering the Earth as a carrier of the clock in a gravitational potential that changes across the eccentric orbit of the Earth around the Sun. Moreover, there have been lots of proposals to use a nuclear clock to search for dark matter, specifically in the field of ultralight scalar fields, searching, for example, for oscillatory variations of fundamental constants, looking for topological dark matter, either in transient signals, where you would use networks of very precise synchronized clocks, but also, and maybe even more stringent limits can be derived from non-transient variations of fundamental constant, where you regard the back action of the ambient matter on the scalar field. All that has been over the years detailed and outlined in lots of very detailed theoretical papers. On the more practical side, one could improve the precision of satellite-based navigational systems like GPS in the US or Galileo in Europe, down to the centimeter, or let's stream to the millimeter scale, which then would give new perspective on autonomous driving, freight component tracking in industry, you name it. There's lots of applications coming up on that. Or one could consider such a clock as already atomic clocks at the moment, where the clock precision is of order of 10 to the minus 18, as a 3D gravity sensor, as the relative change of the clock frequency is related to the change in the gravitational potential, about 1 centimeter related to 10 to the minus 18. So precise and fast measurements, for example, of nuclear clock networks going below this limit could even then be used to monitor local changes of the gravitational potential, for example, due to volcanic activities or tectonic plate movements in a very early stage, actually. And these intriguing perspectives now gave rise to increasing activities worldwide. And here you see, I hope I have not forgotten too many of you who may be outside and not feel yourself here represented on this map, but I tried to compile all the groups that worldwide on theory, on experiment are nowadays working in one or the other way towards thorium-229 based nuclear clocks. And you see it's an increasing number over the years, and in many places here you find also complementary approaches, and this number of groups is still growing. Yeah, so what did we learn over the years? Starting now from this very first indirect conjecture, which was done in 1976, where from conventional gamma ray spectroscopy in nuclear physics to give a consistent picture of, at the time, the nuclear level scheme. That was the aim of the spectroscopic search, but it could only be achieved if people at the time assumed a doublet in the ground state, as they called it, so a very low-lying first excited state, which was just an indirect conjecture, which stayed for a long time, and people searched for it in very different technologies and energy ranges even. But it took a long time, almost 40 years, to have a direct first in identification, but not in the photonic, not in the radiative decay branch, but in the internal conversion decay branch, which means that the excitation energy of the nucleus was transferred to a shell electron, to an inner shell electron, which is overlap with the wave function of the nucleus, and energy is transferred to this electron. The electron is released. You can measure it. It's a conversion electron. And the way it was done was following alpha decay of uranium-233, because if you want to look at this decay, you need somehow to populate the isomer, and as long as you don't know the energy, you cannot do an optical excitation, an optical control, which of course is the goal finally. But as long as this is not available, we have to use what nature gives us, and nature gives us uranium-233, which is an alpha emitter that decays into thorium-229, fortunately not just into the ground state, but with a 2% decay branch into the isomer. And this 2% is actually what for decades people have lived on, and we still live on that, to populate the isomer and then measure our spectroscopic and characterization temporal, for example, measurements. And this first identification was done in this conversion electron channel. And of course, now that you were unambiguously convinced that this isomer exists, and we had in the meanwhile, before even theoretical papers that diffuted the existence and questioned it, but this is now rock solid. And from that on now comes a characterization of the properties of the isomer, looking, for example, at the half-life. The neutral isomer gave a half-life of 7 ± 1 microsecond, which is very much in agreement with the theoretical expectation for the conversion coefficient, so the ratio between gamma decay and conversion decay, which means that you have to suppress the internal conversion electron decay channel by 9 orders of magnitude to have a chance at all to see a photonic decay. And that is a really harsh condition to fulfill. And it took another long time to see, as you will see soon in my talk, how this can be achieved nowadays. Of course, once you then look forward and say, at some point we will have a laser, we will have the excitation by optical means, but we need a method to identify whether we did the excitation at all. And here comes the hyperfine structure into the game, as it was already early on a proposal put up how to identify a nuclear excitation to the isomer. And this relates to, well, as we will see later, some kind of double resonance experiment, but all is based on the knowledge of the hyperfine structure. So according to that, we need as well knowledge on the hyperfine splitting. And this was achieved by collinear laser spectroscopy, where we in Munich, from the nuclear perspective, teamed up with our colleagues from the German Metrology Institute, from the PTB, which then, with their laser spectroscopic experience, contributed to this joint venture that finally ended up in revealing the isomeric hyperfine splitting. It gave the nuclear moments, the electric quadrupole, the magnetic monopole, dipole moment, the charge radii. So this is all ingredients that also are important if we want to characterize and quantify the sensitivity enhancement factor for characterizing temporal changes of the fine structure constant I mentioned before. And finally, as well, until 2022, the last year, those numbers here were then the next step that was achieved in terms of constraining further the excitation energy by different means. We did the internal conversion decay measurements, so measurement of the energy, basically, of the conversion electrons, measure the spectrum in a way of a retardation magnetic bottle spectrometer. those who know about this neutrino experiment running in Germany, in Karlsruhe, Katrin, looking at the mass of the neutrino, the endpoint of the tritium beta decay, they have a huge magnetic spectrometer, and ours basically, I called it always a mini Katrin experiment, which has the same retardation magnetic bottle properties as the big one, and it allowed us to derive the excitation energy here to 8.3 electron volts. Colleagues in Heidelberg and together with people from Vienna, they had a microcalorimetric approach and came up rather soon after to a value which is within errors compatible with ours. And if you combine those two values, you get this 8.2 electron volts, which until a recent measurement, which I will show soon, was then the best value that was for more than 40 years after its first conjecture, constraining the energy and giving also an indication on the type of lasers that could be used. Before, the wavelength was more or less conjectured to be around 160 nanometers. So one could still have the hope that there would be CW lasers available. With this value, 150 and below, maybe even nanometers, this was excluded, at least for the time being. So one has to look into different concepts of developing a laser system that would suitably be used for an all-optical control. Yeah, so what are concepts for direct laser spectroscopy on the thorium isomer? So first of all, one could think about a solid-state approach, where you implant the thorium nuclei in a large bandgap crystal. Large bandgap means larger than the excitation energy. Then you would forbid the decay branch of the internal conversion channel. You would excite the isomer with a BOV laser light and observe the photons from the isomeric decay. That's an approach that is pursued in Vienna by the group of Thorsten Schumm, at UCLA in Los Angeles by Eric Hudson. One could combine such a solid-state-based approach with the internal conversion measurement I just showed before, but now implanting on the surface, or a solid surface approach, not a bulk crystalline approach. You deposit a layer of thorium on some substrate, and then the internal conversion decay is allowed because the band gap now is smaller than the isomeric excitation energy, because there will soon be neutralization on the surface by grabbing electrons into the isomers, the ionic isomers. You would again then isomerically or excite the isomer by UV laser light, but now you look at electrons from the isomeric decay. This is pursued in Gila. Junier is pursuing that with his colleagues, and also Eric Hudson has a project in this direction. The third approach is the ion trap approach, where you have ions stored in a Paul trap in vacuum. The internal conversion decay is forbidden. You have a large ionization potential, which is larger than the ionization energy or the excitation energy of the isomer. You excite with a VOV laser. You observe the hyperfine shift of the electron shell, which is induced by the nuclear spin change, and you look now for photons from this the excitation. And this is an approach that at the German Metrology Institute, the PDB in Braunschweig, Eckhard Peik and his group is pursuing. We are doing that in Munich, and also it's an upcoming project as well at the University of Mainz. So there are different complementary approaches. But what is still missing for this solid state approach, for a long time missing, is the radiative decay branch. So the photon spectroscopy of these radioactive decay chains, where you populate your isomer in a radioactive decay, you implant then in a VOV transparent large bandgap crystal to have this suitable, probably in the 4+ charge state chemical environment that suppresses the internal conversion channel. And then you would look for the vacuum ultraviolet spectroscopy of 100-something nanometer photons from the radiative decay. This on the basis of the alpha decay of uranium-233, which was the predominant, only possible for a long time population path, remained still up to date, unsuccessful. But now one can think of a new approach, and this new approach is not based on uranium-233 anymore, but you could use a more short-lived actinium-229. which of course then cannot be just bought as a calibration source by a company and you can use it in your laboratory, but you have to produce it online using an isol technique, isotope production online, as we will see, for example, at a facility at CERN. And then you produce it either directly or, as we did in a larger collaboration at CERN, implanting francium as the initially produced beam, which then decays into radium, which then beta decays into actinium, and implant that in a calcium fluoride crystal. So the first two decay steps are short-lived, only a few minutes, while the actinium has a half-life of about an hour. So you can quickly wait for the decay of the grandmother, and then you're starting to implant, then you have implanted the mother, which then decays into the daughter, which is the thorium isomer, and then you will be able to detect, hopefully be able to detect the radiative decay of the isomer into the ground state by the emission of a photon. So that is the conceptual idea behind. So go away from the alpha decay, go into the beta decay, and what you have to do then, you can embed into a large bandgap crystal, which is magnesium fluoride or calcium fluoride. The advantage is you can interrogate many nuclei at once, but you have to make sure that you substitute your thorium by implanting into a substitutional lattice position, which then only, because it's then in a fixed charge state embedded in the lattice, give rise to a suppression of the internal conversion decay, and by that then allow for the radiative decay. If it would be in an interstitial position, only then you preserve the large band gap. If you are in an interstitial position, like here, you would see there would be states appearing in the band gap. They would open up the conversion decay channel, and then you would emit a rather conversion electron than photons. The benefit of this actinium-based technique is immediately seen if you look here, for example, as this comparison. The recoil energy of the alpha decay is large. It's 84 keV, so it's a rather violent process. It changes the electronic shell, it liberates electrons, and by that it opens the internal conversion channel. While the actinium, with only about less than 6 electron volt recoil energy, keeps the, crystal structure as it is. Moreover, the implantation or the population probability, which is the 2% I mentioned before, into the ground state or into the isomeric state from all different feeding states at higher energies, is increased to 14%, so considerably also in the beta decay in actinium-229. So you have an adiabatic decay situation, let's call it, and a higher population probability. So all that is very beneficial if you go to actinium. And this actinium actually can be done at an isol facility. So you need to create it in a nuclear reaction. For example, at CERN, where you have an accelerator that produces, not the big one, of course, but one of the pre-accelerators, which produces 1.4 GeV protons, you impinge on a uranium carbide target, which is robotically, because it's very hot temporally, from the temperature seen and from the radioactivity. So it's a well-shielded, robotic-oriented target unit, something like you see here. And there you create spallation reactions. The spallation products, they diffuse in a transfer line out of this hot, 2000 degrees, basically hot target. On the surface, they get surface ionized by the hot temperature, and then you have the different species that were diffusing out, amongst them francium and radium, and those are the short-lived predecessors of actinium, which then decays into thorium. So that is the basic idea, and you do that at this Isolde facility, where you have then, after the target and after the production of this very complex cocktail of different spallation products, you send them through a mass separator, which then allows to select specifically the mass of interest. And then you guide that into a setup, which is rather compact at the end of a beamline here at CERN, just at the end of this beamline, you put the setup, which is basically showing here a VOV spectrometer. So the beam comes, is implanted with about 30 keV kinetic energy into different kinds of crystals. So it's sitting on a target wheel. You implant for some time, then you turn the wheel, bring it into the entrance position of the spectrometer, so in front of a grading spectrometer here, and you have an entrance slit. And then you have with a collimation mirror standing on the grading. The grading can be scanned, and you look at a PMT, a photomultiplier. What is the spectrum that you get there? And well, it's a very compact setup. You also have some other gamma ray detectors that monitor the incoming activity, and by gamma spectroscopy can normalize then the incoming flux. And here the target wheel shows the type of targets, the type of crystals that were used: magnesium fluoride, calcium fluoride, commercially grade slabs of VOV transparent material, except here one a little bit more specific calcium fluoride crystal, 50 nanometer, very thin, and by that adapted to minimize background coming from Cherenkov and radioluminosity, which then helps also to improve the signal-to-noise ratio. So what was the outcome of the measurement here? You see here the comparison between magnesium fluoride, calcium fluoride in different thicknesses, in the different colors here. And fortunately, in all of those crystals, a signal appeared rather soon, around 148 nanometers. For this not very high quality grade calcium fluoride, there was another signal seen at larger wavelength, 190, 185 nanometers, which is basically a crystal defect in that material, so a color center. But what is important here, in all of these different crystals, we see this structure, and the comparison now that gives us confidence about the identification is when you switch your mass separator to mass 230. So basically, then it's not 229 francium and radium, but 230, which then decays into actinium-230, which then decays into thorium-230, which has no isomer. And then if you had the same efficiencies, the same reaction properties, you would expect the type of here dashed line signal height, which is clearly not visible. So there's nothing in the mass 230, while the signal is clear in 229. So that's an ideal identification that we really saw here, the photonic decay of the thorium isomer for the first time, with a wide spectrometer slit on the left-hand side, with a larger or a reduced slit entrance width, and enhanced the resolution here in this 0.5 millimeter slit entrance. And this was recently just published a few weeks ago. You scan that many times, you make a whole series in all crystals, and you have the series of values that you extract from that shown here. And the result, if you make the average and look at the systematic and statistical errors here, the finding is it's compatible with all the values I showed you in the initial slide. So the internal conversion and the microcalorimetric value, but the precision here is improved by a factor of 7, and those are the numbers that I showed you initially. So we are now at a value of 148.7 around nanometers, which is very important for the VOV laser developments. And the time evolution as well is what could be measured here in a way that the decay curve in the gamma peak could be derived with a half-life of 670 seconds. But one has to be aware that this is a half-life which is embedded in a magnesium fluoride crystal. So basically one has to scale that with a third power of the index of refraction. If you adopt that it's happening in the bulk, and let's assume that for the moment, then the index of refraction, 1.55 at this wavelength, would give a vacuum half-life of around 2,500 seconds, which would be compatible by a factor of 2 of what theory with large uncertainties predicts at the moment. So it's going in the right direction, but it still needs a direct half-life measurement in a bulk trap that allows for large storage times, which has to be a cryo trap. And this is exactly what we are preparing in Munich at the moment, and I will show it in a minute. So where are we at the moment? Nuclear spectroscopy in this diagram is in the upper part. What is shown here is the uncertainty, the transition frequency here giving in hertz, or the fractional uncertainty of the clock frequency on the right-hand side. So we are still, and we have to concede that, 10 to 12 orders of magnitude away from what is useful for a clock. So we should not talk anymore in the future in electron volts, but in spectroscopic frequency units of kilohertz or even hertz. And so we have to bridge this gap here down, which sounds a lot to do. Of course it is, but we think it can be done basically in somehow two large conceptual steps. So the first 5 to 6 orders of magnitude could be gained by scanning the frequency range that we are now having identified and constrained with a broadband laser system, which is existing of order gigahertz bandwidth, constrain the search range. Before then, VOV, for example, frequency comb lasers, which are either existing already or under development, can take over and narrow down then to the kilohertz or even below regime. So that is the development that is going on, this pivot point at the moment that goes from nuclear spectroscopy into laser spectroscopy. That's where we are at the moment. Yeah, so there's the two search strategies I briefly mentioned. So you can start with a high-power broadband laser that here tries to scan the nuclear resonance and find it. So this is for an initial search. It will allow then for shorter scan times. Of course, it compromises on the frequency resolution. This is ongoing at UCLA and in Germany at PTB, the Metrology Institute. Or you can use a frequency comb, which gives you a precise frequency determination, but of course at the expense of longer scan times. And this is the approach that Junier is following, that Thorsten Schumm is following in Vienna, and we are following in Munich. Yeah, as well, we need a platform for all that, but we also need a platform to catch up with a still missing ingredient of the bulk property, which is the ionic lifetime, which is an ingredient that is needed also to develop the solid state clock. It needs a longer storage time, which basically needs, from a technological point of view, a better vacuum. So we are setting up a cryogenic Paul trap, which is the platform here also, as you see it, for laser manipulation. The ionic lifetime measurement will be done via hyperfine structure spectroscopy of the triply charged thorium isomer. You see here the ingredients of this Paul trap. And the production and the generation of the isomeric beam, just to recall, will be given by buffer gas cell, where you put the uranium source in. So for this experiment, we are still recurring on uranium with all its decay products, which will then be stopped in a gas atmosphere, in the buffer gas, will be guided by electrical fields towards a nozzle, will then be extracted into a radio frequency quadrupole. The carrier gas is pumped away. There is buffer gas cooling, phase-based cooling here. In the subsequent quadrupole mass separator, the daughter nuclides are filtered out, and you're ending up with a selectable charge state of thorium, either in the ground or in the isomeric state, which then will be sent to the cryo trap. So that is the basic production principle if you start with uranium-233. And the general setup is shown here. So this is the gas cell schematically shown that then extracts into the cryogenic cell or the cryogenic Paul trap, which is operated at cryogenic 4 Kelvin. It has heat shields here, 40 Kelvin and 4 Kelvin. From the right-hand side come, because we want to have sympathetically laser-cooled ions stored in our trap. So we have a laser ablation source that comes from the right-hand side, goes through a bender, goes again through an RFQ and a QMS to purify, send it here in, and then comes the cooling lasers for strontium 88+ laser cooling, and the spectroscopy lasers looking into the hyperfine structure. And you look at the fluorescence, all is stabilized. All that is ongoing to be set up at the moment, either under commissioning or already working. So that is an ongoing project that we are pursuing. Moreover, of course, the most challenging part is the laser that finally should drive the transition. So the VOV frequency comb laser, which is under development. You need to do a frequency comb based on the 7th harmonic. As we have no CW lasers available for this frequency range, at least nowadays yet, and for some years I would expect it to stay like that. So you start with an infrared frequency comb, you amplify it preferably by a fiber amplifier, send it into a nonlinear pulse compression. So spectral broadening gives you a compressed spectrum around 50 femtosecond pulses. And then you send it into an enhancement resonator where you then focus onto a xenon gas jet, generates the 7th harmonic at around 148.7 nanometers, with the goal of achieving as high as possible power per mode, certainly more than one, hopefully in the area of 10 nanowatts per mode. And this is then sent to the spectroscopy chamber, to the Paul trap, where it will then be used to excite, at first to search for the resonance and later on to excite the resonance for a clock operation in a first prototype. So that is being built and developed by colleagues together with us at the Fraunhofer Institute in Aachen, the experts on this type of laser development, and we hope it will be operational early next year. So all that is I showed you a very synergetic concept that we follow with this quest towards the nuclear clock. As you combine very different fields here, I don't list all of them here. You see how many different disciplines put together their expertise in coming to a conclusive, first building the nuclear clock and then applying it. And of course, on the way there's lots of fundamental and technology goals, very ambitious goals: perform the first laser excitation of the nuclear transition, define the structural parameters, achieve a narrow line width of the VOV laser, quantify the sensitivity to fundamental constants and their temporal dependencies, measure the isomeric energy finally to more than 12 digits, at least demonstrate the nuclear clock, demonstrate the solid state clock scheme as well, not only the trap-based one, and then apply it for fundamental tests and even search for dark matter in the end. So that is actually what a European project has embarked to, funded by the European Union. It's called a Synergy project, and this is truly by this interdisciplinary approach what it is. It combines theory and experiment, nuclear, laser, metrological science. Nobody can do that alone, so we joined forces with groups from the Metrology Institute from Vienna, from theory side, Mariana Sabronova, Adriana Palfi, from the laser side, the Fraunhofer Institute, Johannes Weidenberg. So there's lots of people with different expertise contributing. Yeah, and that finally brings me now to my summary and conclusion. So I showed you the achievements in recent years on the identification and characterization of the isomer, culminating now for the first observation of the radiative decay mode just recently. Ongoing activities and next steps are to measure the ionic lifetime, to identify the nuclear resonance with laser spectroscopic precision, to work on determining the sensitivity enhancement for the fine structure constant temporal dependence, quantitatively develop further doped crystal approach in the radiative channel in the internal conversion decay branch. There is next week the next experiment at Isolde at CERN starting that will refine the previous data, hopefully with more and more controlled systematic uncertainty. And of course, there's lots of ambitious goals lying ahead, like for the first time have a nuclear transition excited by a laser, improve the sensitivity to nuclear physics, or search for dark matter candidates. And there's a list to be expanded on that. And with that, I want to give credits and thanks to all the collaborators at the moment and in the past on this project. And I want to thank you for your attention.
Thank you so much, Peter. Really impressive results. And since I'm chairing, I want to use this opportunity to ask the first question. And my question is about inhomogeneous broadening. What you would expect it in your crystal my concern is because you are implanting and also some hypophyte structure is present. So what would be your expectation for this?
Well, at least for the surface approach, where you then look into the electrons still, you would be limited by the Doppler broadening around 10 to 15 kilohertz, something like that.
10 to 15 kilohertz?
Kilohertz. That is at least for the moment a limitation. That yeah. In the trap approach, you can certainly go below that, but there you have only few ions. We are talking about maximum 2 to 10 ions, because it's sympathetically cooling, and you have only this 2% decay branch, so you have only a few ion approach there. While, of course, then the purely solid state approach gives you it gives you the advantage of up to, let's say, 10 to the 18 per cubic centimeter dopant, which gives you, all the advantages of improving on the Allen deviation over short coherence periods. So one has to see which of these approaches will in the end win, which is more from a technological point of view, from the more metrological point of view, the most to be favored. At the moment, we are still struggling at technological phases before coming to that point, but this gives us, let's say, a ballpark coming into, let's say, a few hundred hertz in the trap, single ion trap approach in the next few years, let's say. And then, of course, we have to work on improving that on a level that is competitive to what the marvelous experiments on the atomic clocks, the lattice clocks, have reached already today.
I see. Because it's 10 to the 18 dopants what you have, it's not a stoichiometric crystal, so that is my concern about inhomogeneous broadening, right?
Well,
what about hyperfine structure? You mentioned that you measured the hyperfine structure. What is the width of the nuclear magnetic resonance, or what is the characteristic?
Well, this is not in the crystal measured. So
it was not in crystal. I see.
No. This was in the
liquid.
This was in the Paul trap, actually.
In
the Paul trap, even
it's different.
under optimum vacuum conditions. So therefore, I think we cannot compare that. But if you say it's not a stoichiometric crystal, well, at least the implantation that we could achieve at CERN with a rather violent 30 keV implantation revealed by electronic channeling that more of order 80% of the isotopes were placed on lattice sites, not yet using the technique of annealing, which could improve that, because this would have probably influenced the systematics of the spectrometer. So this is something coming up. So one can already prove at the moment that an implantation, which is supposedly quite violent, achieves a high implantation on lattice site. The same comes from the growing of the crystal, what the colleagues in Vienna are following. They grow their crystals into calcium fluoride or magnesium fluoride, and initially they have a rather moderate optical quality. But now they have developed a technique to fluorinate the crystal after that, and it drastically improves the optical quality. So there's lots of things going on.
It's really impressive how it is developing.
So the optical quality is improving, and it has not yet reached the end.
And the frequency of the transition, it's really great that you know that it is around 8.3 electron volt. But you mentioned that in one of the experiments, not in your group, but in the other group, it was about 8.1. What would be the difference? Is it because of some error? It's hard to say.
Well, the error margin was 0.7 electron volts. So I think even within 1 sigma, they were overlapping. And it could, I would not worry about even if it would be in the 2 sigma range.
Yeah. Other questions? I don't see any raised hands. Please unmute yourself if you want to use your chance to ask the question. Well, I don't see any. So again, thank you so much for this very, very exciting, very interesting talk. Thank you, Peter.
Thank you.
So now we have to proceed. And okay, let me share again my screen. Okay. So I'm really happy to introduce our second speaker in our session, Jun from NIST, Boulder. And he received his bachelor degree in Shanghai Jiaotang University, his master degree actually with Martin Scully, University of New Mexico, his PhD with John Hall, University of Colorado in Boulder. And he did his postdoc with Jeff Kimball. So it's a wonderful collection of the supervisor, very good choice. And since 1999, he is connected to NIST, where he is a full fellow and a group leader. And he received a huge number of awards. I mentioned just a few of them, including LPHYS' Rabi Prize Award in Atomic Molecular Optical Physics, Norman Ramsey Award, very recent Breakthrough Prize in Fundamental Physics last year. And in 2011, he was elected as a member of the National Academy of Sciences. And so what he did so good so that to get so many awards? Well, he did really something remarkable. He's basically the world leader in quantum metrology. So he produced the most stable lasers and optical frequency comb and ultra-cold atoms and molecules, and use these tools to do all kinds of fundamental physics and quantum information science. And his strontium optical lattice clock probably is going to be very soon a new frequency standard. And so we're going to learn today from Jun about new development, which are on the borderline with optical clocks and quantum effects. So let me close my sharing.
Olga, thank you very much.
You're welcome, Jun.
Thank you very much, Olga, for your very kind introduction. And hopefully in the next 40 minutes, it will give you some update on what's going on. And thank you, Peter, for the wonderful talk on nuclear clocks. I think that got everybody motivated, that the why clock physics is interesting. So I'm going to get started. Let's see if I can get a laser pointer. Yeah. So I'm going to tell you a little bit about the latest work on optical atomic clocks. But since this is a laser physics conference, I'm going to start with telling you a little bit about lasers. There are a new generation of very stable lasers thanks to decade-long collaboration between our group and a German standards lab that Peter also mentioned in his talk, PTV. Many wonderful colleagues there, particularly Pl.2 and Fritz Rieler. We have been collaborating since 2006, 2007. The generation of so-called cryogenic crystalline cavity made out of a silicon crystal that has very high mechanical Q, has very high Young's modulus, and most notably has a zero thermal expansion point at 124 Kelvin or 16 Kelvin and so on. So it's a material that allows you to build ultra-stable optical interferometers that will give you some of the most stable lasers to date. For example, here's a beat signal between two independent lasers locked on two different cavities, one at Jella, one at PTB. At the time, the two cavities were together. And you can see the beat line width of 8 millihertz out of a 1.5 micron lasers. And the optical coherence time is now approaching tens of seconds. With the optical frequency comb over the years, we can, with one stable lasers, you can transfer that phase coherence across the entire visible spectrum. And therefore, the frequency comb is not only a tool that we use to build atomic clocks, but it's a tool to really digitally synthesize the electromagnetic spectrum that allow you to do novel spectroscopy, including nuclear spectroscopy that Peter mentioned, with the stable lasers driving the entire frequency comb. And in our laboratory, for example, we can have a silicon cavity working at a 1.5 micron, but through the frequency comb, we can transfer that phase coherence to the so-called clock transition of strontium at 698. And you can see the local oscillator, the laser that we use at 698 to probe the strontium transition can be compared with a 1.5 micron laser, achieving a stability of just a few parts times 10 to the 17th, between 10 to the 4 seconds. So those are incredible tools that allow us to do quantum metrology. And I would just want to give you a quick update of what's going on with the next generation of, as we continue to try to march towards better cavities, better laser coherence, and so on. One latest technology that we are using is so-called crystalline coating. Instead of using amorphous coating, that's giving rise to the fundamental thermal Brownian noise. And the idea was, just like a silicon cavity, if we can also turn the optical coating into a crystalline material, we should be able to reduce the mechanical loss angle, therefore increase the Q and reduce the fundamental Brownian noise contribution. And so we have been experimenting with these crystalline coatings inside the silicon cavity, and I've shown here some fluctuations associated with coating material, either due to the local fluctuations due to the thermal Brownian noise, or some global fluctuations of a system which can not be averaged away by using larger beam waste. And what's really interesting is that these crystalline coatings are indeed, because of their high mechanical quality factors, are expected to give rise to another factor of 3 or 4 enhancement of the laser stability, approaching 1 times 10 to the 17 for our particular cavity as we operate today. During the initial search for laser stability using these crystalline coatings, we actually discovered a birefringent noise that's novel, and we verified that indeed there's a thermal Brownian noise of these coatings much lower than the conventional amorphous coating. However, we also discovered that there's a new global noise that's associated with the semiconductor material. That's something that the research work is ongoing and has a major impact for anybody who's willing to build precision interferometry, because that contributes to the noise of your interferometer, including LIGO. And so this work is ongoing in collaboration between PTB and JILA, and try to see whether we can continue to advance the state of the art of stable lasers with coherence approaching a few minutes. But one important aspect that Peter also talked about is using an ultra stable laser like ours. You can use this to drive, thanks to the frequency comb, to digitally synthesize electromagnetic spectrum. You can actually, not only in the visible part of the electromagnetic spectrum, but also in the infrared and in the ultraviolet. You can now producing frequency combs that can be phase coherently connected to these very stable lasers in the visible range. And such capability gives rise to new scientific opportunities. The laser physics conference, I think I participated many years ago, has always been driven by the idea of when you have a new tools in lasers, you often open up new chapters. And the nuclear clock is just the latest example that hopefully will break through that, being able to start to discover nuclear physics with lasers. That would be just amazing. But as we continue along the work that the pioneers laid out back when the laser was first invented, I think the laser spectroscopy field itself is still flourishing because of the new tools of lasers continue to become available. The latest example include, for example, we can for the first time understand C60 molecules, this incredibly symmetrical molecules. We can understand the symmetry breakings, ergodicity rising from 60 bosons interacting with each other under very symmetric arrangement. You can even use the frequency combs in the infrared for medical diagnosis. Recently, we were able to use the frequency combs to measure people's COVID with 85% accuracy. Or, as Peter mentioned, as we continue to develop better tools in the ultraviolet, including vacuum ultraviolet and extreme ultraviolet, but even into the soft X-rays, it's going to open up a new scientific landscapes, including driving nuclear transitions directly. But for my talk today, I'm going to tell you a little bit about atomic physics, how we are using atoms to build some of the best atomic clocks today. And I want to make just a quick comment about quantum metrology, since Olga mentioned this in her introduction. As we design better and better clocks, we want to find quantum systems that have incredible coherence time. And that's part of the motivation behind the nuclear clock, as Peter mentioned. But another really important point, and I think we shouldn't forget, is that in order to push the precision forward, it is very helpful to have lots of atoms, or whatever the quantum particles you are using, simply because you can keep the measurement precision much higher if you can average over many quantum particles at once. And that gives you a large count rate. And over the past 20 years, I think one of the very exciting development is actually the merge of quantum antibody physics and quantum metrology. That's because as we use more and more quantum particles in our system, you have to start to understand these quantum particles are going to interact. And how do we, on one hand, satisfy our greed of continue to increase the count rate, at the same time, continue to be able to understand systematics when these particles are interacting with each other. Or maybe even to a point, by understanding it, you can harness these quantum antibody systems, building entanglement, so you can actually achieve quantum enhancement of your measurement precision. And that really is one of the most exciting frontier at the moment, where the precision frontier meets the quantum frontier. And the field of the atomic clocks has been rapidly progressing, as Peter also mentioned earlier. Well, thanks to large part of this quantum control that provides this very high Q optical transitions by quantum state engineering of atoms, laser technology where optical coherence is approaching a minute, frequency comb allow you to synthesize electromagnetic fields, and then quantum gas, ultra-cold atoms and molecules now allow us to realize many-body states for metrology. And so over the past decade or two, the optical atomic clock has now achieved astonishing precision of a few parts 10 to the 19 and accuracy of roughly speaking of 10 to the minus 18. But the field is still moving rather fast. And just because of the power of the quantum synthesis of the matter that uses for metrology, where all the motional degrees of freedom, as we can think about this, right? As you're approaching 10 to minus 18 level of clocks, you actually have to consider the second order time dilation effect. Any motion of these atoms and molecules and so on will contribute to the time uncertainty. So these have to be very precisely controlled, in addition to many other systematic uncertainties that you may have. But thanks to these quantum metrology efforts, I think at this time, over the past few years, the measurement precision of the clock has been advanced by another factor of 50, now reaching mid 10 to minus 21. And I think this will continue to increase in the measurement precision. The accuracy as being evaluated at the moment, I think very likely will approach the mid 10 to the 19. So the field will continue to advance thanks to this large effort of being able to put quantum metrology in the context of quantum antibody physics. And that's really the theme I want to tell you about today, to a point where we can understand many-body Hamiltonians to understand systematic effects at the 10 to minus 19 level. And then we can turn this around by controlling the many-body Hamiltonians to enhance the measurement precision. So let me start with this basic idea of decoupling spin and motion. Well, spin is, if you think about two-level system, ground and excited state, that two-level system you can think of as a pseudo spin half system. And as any metrology work, if you want to look at the internal degrees of freedom, the spin degrees of freedom, you want to make sure your spectroscopy effort is not being influenced by the motional degrees of freedom, one of which, the most important one, is a Doppler effect. So this idea of so-called magic wavelength trapping is based on the concept that the ground state, excited state of the atom, as the atom being confined in a field of optical lattice, the AC stock shift between the ground state and the excited state experience exactly the same AC stock shift, such that you can see the motional degrees of freedom and the internal degrees of freedom are decoupled. In that case, when you do spectroscopy, you can actually look at the so-called carrier transition that is not influenced by the AC stock shift of the motional states. And on the other hand, the motional effects, of course, are still there, but they are manifested as the sidebands, the so-called blue sideband, the red sideband. The blue sideband is exactly spaced apart from the carrier by the transition frequency of the motional degrees of freedom. And you can think of the particles confining a harmonic potential, and it can gain quanta when you drive the transition from ground to excited state. And that's the blue sideband. The red sideband is suppressed in comparison. The reason is that because if you cool the atom to the quantum mechanical motional ground state, there is no lower motional states below the motional ground state. Therefore, the red sideband is suppressed. Here you can see that the temperature of the atom is still occupying a few emotionally excited state. That's why the motional sideband is not zero. But later on, I will show you how the cooling works better, where the completely the entire motional degrees of freedom is frozen at the ground state. And just to tell you that such magical wavelengths, of course, needs very careful evaluation to understand that on one hand, you can trap these atoms in the motional ground state. On the other hand, the very fact of the presence of the trapping field itself does not contribute to the uncertainty of the clock at the level of field parts 10 to the minus 19 level. And that's being evaluated and see the recent publication, for example, showing the AC stock shift is evaluated at 4 parts 10 to the minus 19. And when we put atoms inside this one-dimensional optical lattice by simply forming by interfering counterpropagating laser field, you can have a stack of these pancakes where a few dozens of atoms are trapped in individual pancakes. If I zoom into one of those pancakes, you can see a few dozen of atoms are located confined in this two-dimensional optical trap, and the atoms are moving along in the transverse direction, but in the vertical direction is completely frozen. So the transverse direction has some motional quanta. These atoms happen to be fermions. When we drive the clock transition, you're looking at a pseudo spin half system that can be described by this block sphere, where they're driving from ground to the excited state. And in fact, what we often do is put them in coherent superposition between ground and excited state. And you look, and after it evolves for a while with a laser field, then you probe this again. This is conventional Ramsey or Rabi spectroscopy that allow you to measure the phase slippage between the laser field and the quantum pendulum of these atoms. So as we do this, these atoms can actually interact, even though these are fermions. And with the fermions, of course, what we need to do is to have a wave function to be anti-symmetrized. So if you have internal degrees of freedom, GE plus EG being symmetrized, then their transverse motional degrees of freedom represented by the motional quanta has to be anti-symmetrized, and this is what we call the P-wave interactions. Typically, P-wave interactions are exceedingly weak, but because of this incredibly precise measurement precision of clock, we can actually measure these effects quite well. And in fact, you can think about this as this P-wave interactions are very weakly dependent on these motional degrees of freedom. Therefore, you can think of these pairwise interactions as actually gives rise to collective spin-spin interaction, where the collective spin is nothing but n particles, each with spin half. So total spin is now n/2, this large spin vector, and this large spin vector is connected to each other by pairwise interaction, giving rise to this SZ square term, so-called Heisenberg interaction term. And this can give rise to spin squeezing. In this particular case, also can give rise to systematic effects where the quantum noise become distorted, but it can also move away from the frequency. The frequency can be shifted away from single particle clock transition. So back in about 10 years ago, we decided to remove this interaction effects by confining these atoms in a three-dimensional crystal. And the idea being, instead of having just one interference patterns along one spatial directions, why don't we do that along all three spatial directions, therefore forming this cubic center crystal, as I've shown here. The idea of this is, if you cool the atoms to sufficiently low temperatures, you have a Pauli exclusion principle guarantees one fermion occupying one site, and therefore you wouldn't have these p-wave interactions between atoms because you only can have one atom per site. And you can scale the system up to, say, 1 million atoms. And if you can achieve coherence time of 120 seconds, that's given by the excited state lifetime of strontium atoms, you will be able to achieve a clock precision at 1 second of few parts 10 to the 20. And this was back in 2016 when we were designing the system. When we realized that, we felt quite empowering, because that's the sensitivity people doing gravitational wave detection at the time was relying upon. That basically they had achieved a string sensitivity of 10 to minus 21 to be able to see gravitational waves. And imagine clocks after 100 second averaging time can achieve similar sensitivity of 10 to minus 21, then you can start to dream about using clocks to actually see gravitational waves. And so at the time we were working at 10 to minus 16, 10 to minus 15 at 1 second kind of stability. But I'm happy to say, over the past 6-7 years, we did improve that precision by a factor of 100, now reaching 3 times 10 to minus 18 at 1 second, still fairly far, about a factor of 100 away from this idealistic system that we were hoping to achieve in the future. But this naturally gives rise to a question. You have a very densely packed atoms, one per site, and they're spaced by 1/2 a wavelength. So there's lots of atoms in there. The natural question you ask yourself, being a laser physicist, being a quantum optics person background, you will say, well, there must be light atom interactions must be altered by the fact that you have packed so many atoms close by. And this can give rise to very important systematic effects for clock. And so all the background of quantum optics and quantum physics, many-body physics, now becomes a useful intellectual background for us to explore the systematics as we continue to advance the measurement precision. And that's the story, as I mentioned earlier, that I want to give you a few snapshots on. The first thing is, let's take a spatial image of this atom that's been distributed in this three-dimensional crystal. As I mentioned, if these are fermions, if the temperature is sufficiently low, you should have one atom per site. And when you take a high-resolution image, it looks like a Mexican pyramid. The top is flat. The reason why it's flat is because you can have only one atom per site, and only on the edge, the atom occupation number comes down, and that becomes a thermal. In the middle, it's very much so-called a quantum degenerate system, where you have the band insulator, you have a one atom per site that's occupied. We can apply a magnetic field gradient just to test the system. We can apply a field gradient across the crowd. And as we know, of course, the magnetic field is going to create Zeeman shift. And so the laser interaction with atom now is going to be regulated by the field gradient. And as we can see, excited state, ground state is alternating. That's because the field gradient gave rise to the frequency shifts such that the Arabi frequency is being modulated. And you can actually freeze the atom light coherence as just images of atoms in this optical crystal. So this gives rise to this capability that we can now use this technique to measure field gradient. And I'm going to use this technique again later to use these atomic crystals to measure gravitational potential. But the first thing I want to tell you about is such a densely packed atoms, there will be interactions due to so-called dipole-dipole interactions. And this is something my good friend Michel Lukin anticipated back in 2003, 2004, when we met each other in Moscow. And the one of the ideas that he was proposing at the time was, well, maybe you have to worry about the collective effect, because I was telling him these dipoles are exceedingly weak. As that we are driving the so-called clock transition, the transition dipole moment is at the 10 to minus 6 divide. very, very weak transitions. But if you pack all these atoms, hundreds of thousands of atoms together, and with the atoms basically in their neighborhood, because the distance between them is only one wavelength apart. Therefore, you could give rise to so-called cooperative Lamb shift, that some of those effects that Marlon Scully talked about back in the 90s. So this is also related to the original Dickey model, when you have carefully arranged arrays of atoms, and when you essentially you can think of each dipole moment is a radiating radar, and they are connected by phase coherent arrays of excitations. They will give rise to many interesting phenomena. And in this particular case, we actually drive all the atoms in the coherent superposition, so we're in the so-called many excitation limit. And as we propagate the clock laser inside the crystal, we can change the angle, therefore exciting these atoms at a different phase shift, as being displayed here by different colors of the donuts representing the dipolar pattern of the radiation. And the distance between them is roughly on the order of 1.2 times the lambda. So when they have a collective interactions, you can actually see, depending on the angle of the incidence, you can have the interaction be enhanced. This is Bragg resonance, or you can suppress it by going through the zero crossing point. Therefore, you can manifest this effect by macroscopic interference effect constructively, or you can destructively cancel this effect if you don't want these dipolar interactions to affect your clock accuracy. And so it's a very assuring that we can see those very minute frequency shift at the 10 to the minus 19 level and being able to control it. And here shows the so-called Allen deviation when we measure these dipolar frequency shift, and we can average it down below 10 to the minus 19 to demonstrate the control of these dipolar frequency shifts. And then once we understand it, of course, this can turn into a really interesting controllable tool. So we can drive these clock transitions, and by tuning the angle, we can control the magnitude of this cooperative Lamb shift. But at the same time, what if we actually drive another transition to singular P1 or actually triple D1? These transitions will allow you to borrow the much larger dipole moment onto the triple P0. Therefore, you can enhance the single S0 triple P0 dipolar shift by several orders of magnitude. Here shows the picture that we have preliminary data to show that indeed we can already magnify these dipolar interactions tremendously. And that means that you can turn on this control field to turn on interactions between neighboring dipoles momentarily, and then you turn that off and allow the clock laser, allow the clock state to evolve for a while, and then read them out. So you can use this extra tool to create entanglement or spin squeezing in three-dimensional optical lattice. So I mentioned about dipole-dipole interaction. Let me also tell you about the contact interaction. As I assured you, these atoms are occupying one per site, so therefore the contact interaction should be minimized. Well, that's what we naively thought, but we need to experimentally verify that's the case. What if there's a spin impurity? When I say spin impurity, meaning the strontium atoms actually are fermions with a 10 different nuclear spin state. So there could be a possibility where you didn't spin polarize them into one single nuclear spin state, and there could be different nuclear spin state that can occupy the similar sites. So in this particular case, I want to show, well, indeed, motional states are now quantized and in the ground state in all three directions, as manifested by only the blue sideband but no red sidebands. So the atoms are motionally cooled to the ground state. But if I have 10 different nuclear spin states represented by different colors, well, they are not different colored atoms representing different nuclear spin states can't occupy the same site because there's no Pauli exclusion principle when you have a distinguished particles. When that happens, you worry about, well, what if there's a frequency shift due to the fact that you have these impurity spins that's going to come in and cause problems to your pristine landscape of single atom per site kind of a landscape. It turns out that's not something we need to worry. And that's because the confinement of the individual atoms is so strong. When you put the two atoms on top of each other, they interact so strongly that you can actually have these interaction sidebands well resolved from the carrier transition when you have only one atom per site. And in fact, we can actually go further. Instead of doing just two atoms, why don't we go 3 atoms, 4 atoms, 5 atoms? And all these interaction peaks are very well resolved from the singly occupied atomic transition. So that shows that contact interaction is basically quantized away, just like a Doppler effect. Has been quantized away by the optical lattice. So next, we want to investigate atom-like coherence. And what we found out in 3-dimensional optical crystal, that the coherence time at the time of 3 years ago was limited to a dozen seconds, 12 seconds or so. On the large intensity regime, when the lattice becomes really steep, the coherence time gets shorter. That part we understood, and that's because the atom in the excited state in Pl.2, the excited clock state, can Raman scatter light of the trapping light to depopulating these the excitation in the Pl.2, put them back into the ground state, therefore destroy the coherence. So when you get too much trapping light, that's not good. There's a Raman scattering going on. And the ground state actually doesn't Raman scatter because it's much further detuned away. On the other hand, when you go to shallow lattice, that's a way to avoid the Raman scattering. We also see lower coherence time. And the reason of that is actually due to the fact there are defects in our crystal. For example, this atom, when there's a defect, it can tunnel, and you can watch the animation when this atom tunnels over here. Well, they can occupy there. Another atom, when we try to tunnel to already occupied site, it cannot go because it's blocked by the interaction. But if there is a defect, then this atom will tunnel. And the fact that the spacing between neighboring sites does not equal to the wavelengths of the clock laser, meaning you will experience a phase shift of the clock laser, therefore contributing to dephasing of the system. So that's a problem. How do we solve the problem of the defects? Well, there are many ways to do it. You can create a disorder in your lattice, for example, to try to stabilizing the position of these atoms. Well, another way to do it is simply by, what if we propagate lasers instead of in the horizontal plane, but along the vertical plane? Because there's gravity. The gravity will create will lift the degeneracy between the neighboring sites as a clock laser is propagating between these different sites. These different sites have a different gravitational energy, and therefore the tunneling will be suppressed. And that was the basic idea. And working with the theorists, actually, this is where it's really intriguing, right? That you can then turn this kind of a tunneling problem into a very interesting Fermi-Hubbard model. That's kind of a condensed matter physics model. And here we have also spin orbital coupling, because the laser, as the atom tunnels back and forth between neighboring sites, you pick up a laser phase, since the propagation laser wavelength is different from the lattice spacing. So it's actually quite an interesting condensed matter physics model, but we can learn this and use this to control our quantum system. And if I write down a Hamiltonian for this Fermi-Hubbard model, there's a hopping term, and the atom is jumping from site J to J+1 and vice versa. But there's on-site interaction term. Spin up, spin down represents the two clock states being driven by the Rabi frequency omega, and the J phi is nothing but this spin orbital coupling phase between the neighboring sites. You have a different phase shift. Phi is nothing but the kx term, the phase shift term. So you can actually write down this canonical sort of a Fermi-Hubbard model and understand the dynamics of the system as you're driving with your laser field as you're looking at the clock transition, and understand, well, in 3D lattice, of course, you can also have the freedom of, by tuning different angles. In this particular case, we're tuning the angle exactly perpendicular to the gravity. And so there's this fixed phase shift, and we can put this phase shift in there and solve this Hamiltonian, and trying to find areas where you can avoid the frequency shift, but at the same time create spin squeezing. And one particular example is the following: what if we actually make in the transverse direction have a fairly deep lattice. Therefore, as the laser is propagating along the vertical direction, you can think of arrays of independent tubes like this. It's like one-dimensional tubes, and each one-dimensional tube has very regularly spaced atoms in there, and you can actually use this Fermi-Hubbard model in one-dimensional space, do the calculation, but then realizing, oh, all these atoms on the same plane, in the vertical layer by layer, they're all identical because the laser phase is propagating directly along the vertical direction. So if the laser wavefront is flat, all these atoms in the transverse plane, they all evolve exactly the same. Therefore, you can form a gigantic spin being mediated by the spin orbital coupling in the one-dimensional system. So we can actually, again, create opportunities for spin squeezing in three-dimensional system. So we thought this system is quite interesting. Why don't we give it a try? And in the first trial, maybe we don't want to do many parallel tubes. Maybe we actually remove those tubes, just make it going back to the pancakes, one pancake at a time, and have a laser propagating in the vertical direction. And this gives rise to this the latest system of our one-dimensional optical lattice. In this case, we actually spend much bigger volume by putting the optical field inside the build-up cavity. And this lattice, we made it to be quite shallow to avoid this Raman scattering problem. So the trap depth is 10 times shallower than the traditional one-dimensional optical lattice work that we have been doing over the past 20 years. And so now I'm exaggerating. You can see there's between neighboring sites, there's a gravitational potential energy, which is nothing but mass of the strontium atom times gravity times the wavelength half. That's the spacing between the lattice. That's nothing but a gravitational energy difference between the neighboring sites. Now, this is a traditionally in condensed matter physics, we call it this Wannier-Stock state lattice. Essentially, it's a periodic lattice subject to a force. In our case, the force is gravity. And an eigenstate of such a system is described by the so-called Wannier-Stock states, where it's nothing but you write down the localized Wannier orbitals, the wave function of individual cell, but then you have to connect them through the Bessel function to create this eigenstate, which is actually a stationary state. The wave function is spread it out. And we're going to use this system now to build the clock. And as I described earlier, the wave function is actually spread out because it's so shallow. And we use just a few photon recoil energy to suspend atoms against gravity. And the wave function is spread out to many neighboring sites. So coming back to the idea where we have these pancakes spaced apart by lambda over 2, lambda is the lattice laser wavelength. There's a gravitational energy difference between neighboring sites. The wave function this is the ground state. Well, the wave function is spread out due to the Wannier-Stock states. But we also have excited state. This is ground state, excited state. They have the magic wavelength, so the trapping potential look exactly identical. Now you can drive the clock transition on side I, and that gives rise to this Rabi frequency, very long coherence time. You can also, because the wave function is spread out, you can also drive on the neighboring sites. The J could be as far away as 20. So you're driving a really interesting coherent superposition where the ground state atom is sitting here, the excited state atom is sitting 10 sites away. And you're in this coherent superposition between ground down in the left, excited state up on the right, separated by 10 microns. This probably reminds you already an atom interferometer, because the motional degrees of freedom, the center of mass wave function is not separated under gravity, and the internal degrees of freedom spin is of course evolving as a clock transition. So if you drive these kind of transitions, you can see this is the black line is the center carrier, but there's now sidebands. These sidebands is not motional sideband I discussed earlier. These are the off-site drive, and so sideband frequency is offset from the carrier by nothing but the gravitational potential energy. That's something that we learned in high school, MGH. This is not general relativity effect, it's just the energy difference. But nevertheless, it's really nice to see them very highly coherent signal that we can actually, these are experimental data that can see very narrow transitions. And in fact, it's so narrow, we decided to look at what is the coherence of the system. And because our laser is not quite yet at the level of being able to chase down coherence at a minute scale, then we decided to remove the laser inference by comparing directly the upper half of the crowd and the lower half of the atomic crowd and look at their relative coherence, because that will tell you how coherent the system is actually evolving. And effectively, you're comparing two sets of a pendulum, one's upstairs, the other one downstairs, and see whether they are always swinging in synchronization. And indeed, if you drive these transitions, preparing atom in coherent superposition, you wait 6 seconds, you can see those two sets of coherent superposition are still very much in coherence and very much in phase. If you wait longer, after 30 seconds, you can see that coherence is still there, but it's shown by the long axis of the ellipse. But you can start to see it's opening up a little bit of an angle, and that's because if there's a frequency difference between region 1 and region 2, then of course that frequency difference will give rise to phase shift between these two sets of pendulum, and that's why it's opening up the angle. And we can do that all the way out to 50 seconds, showing the coherence is still there. And this is interesting, there's such a long coherence time, but we can also, going back to when I first started the talk, telling you about in a single pancake, atoms are interacting with a P wave. But now we have the opportunity, the atom can actually interact between the pancakes, because these pancakes are so shallow that not only you have on the single pancake, you have a P wave interactions, distinguishable atom from neighboring pancakes can interact with now the central pancake through the S wave interaction. So that gives rise to this tunability. By tuning the lattice depth, you can actually tune the relative contribution between the P wave and S wave such that interaction can be tuned to be zero. And this gives rise to the capability that we can have many, many atoms, hundreds of thousands of atoms in the system, and yet we do not have to worry about the interaction frequency shift. And this is controlled at below 10 to minus 20 level. And so that's really assuring that we can now go ahead and measure the frequency shift across this several hundreds microns long crowd sitting under gravity. And we can start to measure that there's a frequency shift apparently across the entire crowd. This is not due to this pancake to pancake gravitational energy has already been removed here. That we are driving just the carrier transition, and the carrier transition shows a tilt with respect to the gravity G. And if we plot this slope as a function of daily measurement, what we are showing is essentially the prediction of the general relativity of Einstein, the so-called gravitational redshift of the clocks. When you are closer to the Earth, your clock frequency goes down, and so on. And we can see this exactly matches with that. And the frequency shift is a 10 to the minus 19 level if the elevation change is on the order of a millimeter. We can also directly measure this effect by picking the top half beating against the lower half. Just think of my crowd has two different clocks, the top half clock, the bottom half clock, and just make a frequency comparison. And you can see the frequency comparison goes down all the way to 6 times 10 to minus 21 for each clock. And the gravitational redshift for 100 micron elevation difference is 10 to minus 20. So we can actually now measure the gravitational redshift at a few hundred micron level. It was a clock precision we have demonstrated today. And this similar work actually being going on in my former postdoc, Shimon Kokowitz group at Wisconsin. He's actually moving to Berkeley now. And his work, I think recently also showed centimeter scale gravitational redshift measurements in his lab. So this begs the question, now that the time, as we measure better and better, you really have to start to worry about this picture where the time is so very softly defined. It really depends on your local geopotential. And this begs the question, is it possible that one day we can resolve gravitational redshift on the length scale of the quantum mechanical wave function? What if we can resolve frequency difference between every single pancake, which is spaced apart by the optical wavelength, and remember, we can also create a superposition of atoms between many, many neighboring pancakes. Now you start to look at it, quantum entanglement under the influence of gravity. And this, to me, this is extremely exciting. It's not nothing to do with quantum gravity. It's all weak gravity, but nevertheless, it will be the first time where microscopic quantum coherence, quantum evolution, clocks, and so on will be connected to the macroscopic theory of gravity and through the general relativity. So how do we go there? Because of my limited time, I think I will bypass this slide. This is a slide to measure how to measure single photon mass, but rather coming back to this quick idea that when atom absorbs the photon, the rest mass will change, and it's simply through this equation of energy equals to mc squared, and that means due to the gravity, the ground state and the excited state have effectively different mass due to the absorption of a single photon. And now when you put a Hamiltonian under gravity, notice there's mgz term, but this alpha, which indicates the internal degrees of freedom of G and E, will depend on whether in a ground state or excited state that will give rise to different gravitational shift in your Hamiltonian. So this is starting to incorporating the gravitational effect directly into the single particle Hamiltonian. And it's quite interesting. You can read this paper that written by our colleagues in the University of Hanover, that they can expanding this the term out. You can actually directly show through the single particle physics Hamiltonian the motional redshift, E squared over C squared, you can call second order Doppler time dilation effect at a 4 times 10⁻22 level for our optical lattice system, and as well as the gravitational redshift effect, the effect that I'm measuring over a few hundred microns per site will be actually on the order of a mid 10 to the minus 23. So it's still challenging, quite challenging for us to measure, but these are the effects that's there. You can very quickly derive. But what's interesting is, of course, we can do this many-body physics, as I was talking about, and you can now start to describe the many-body physics where if the Hamiltonian interaction is happening on one pancake, when you're including the GR term, this interaction on the one pancake does not, it commutes with GR, but the interaction between the pancakes do not commute with GR because GR depends on the location against gravity. And so these will start to now influence quantum many-body evolution using gravity. These are the effects we cannot see today, but if we improve clocks by another factor of 50 or so, we'll start to be able to see those effects. And I'm going to conclude. Of course, these are very difficult effects, and how do we difficult challenges? How do we see those? Well, maybe we should put a quantum entanglement into the system. So I'm going to conclude on this particular aspect that that we can build a system that can have movable ensembles, can move up and down against gravity. Against cavity QED, that's a trick I learned from Jeff Kimball. You can do quantum non-demolition measurements to do spin squeezing, and then that allow you to compare clock A, clock B when they're both spin squeezed. And we start to see the impact of that. The spin squeezing can overcome the so-called quantum projection noise limit. So with that, I want to conclude on saying building a clock, and as Peter also emphasized this point, building a clock is not just a timepiece, but it's a probe of our universe. It's a probe for our Mother Earth by doing the geodetic physics and so on. So exciting scientific prospect all around for us to continue to push on this field. Thank you very much.
Thank you so much, June. It's really amazing results. Looked like it's hardly possible to push further your clocks, your stability, accuracy, but you always find a way, and to find also many fantastic applications in fundamental physics. Maybe I want to ask you, well, I think it's going to be really hard to compete with atomic clocks using nuclear clocks, but still there is a lot of new fundamental physics because it's a different interaction which is responsible for nuclear clocks. Mm-hmm. And my question, it seems to me that because you were the first one to develop this intracavity high harmonic generation, would it be possible for you to provide this kind of frequency comb based on it for nuclear clock for Peter work?
Yes, no, Olga, thank you for asking that question. Of course, I think the nuclear clock works is very, very inspirational. As you mentioned, that's because once you open up nuclear physics to explore that, one, just being able to use lasers to change the nuclear transition, that's just super exciting. Second,
Yes.
as Peter mentioned, the nuclear physics really opens up new sensitivities to explore new physics, fundamental physics, which we know there are mysteries out there. So I think that's extremely important. And my statement is about just because you found the transition, of course, it will take quite a long time to be able to develop, because you know the precision really relies on many quantum particles. How do you engineer quantum states and so on? That take a lot of sort of state of the art. But I think nevertheless, being able to see nuclear transition will qualitatively change the field. And because of that, I'm actually very inspired by the work Peter and others are doing. And therefore, as you mentioned, our group has been developing XUV frequency comb since 2004. So we actually have a frequency comb that's being used to scan nuclear transitions right now. And Peter's work that allowed us to narrow down the uncertainty of where the transition could be. I think that's extremely important, because the XUV comb, VUV comb we have, per comb teeth, the power is limited. So in order to scan across this very weak transition, we have to average. But what we have is that these VUV comb has a very good phase coherence. So we are not afraid of the line being narrow, but we are afraid the line being weak. So we need a power. And so the narrower the uncertainty, the more that Peter can confine the uncertainty of where the transition is, the better for us to find it with direct photon excitation. I have no doubt one day somebody will find it, and we would like to join that force right now to see this, because in my lab, if we find it, our VUV comb is driven by strontium clock. So as soon as we find it, it's already connected to the atomic clock. So it'll be very exciting.
Yes, indeed. Yes. Yes. Well, many questions. I think Vitaly was the first one who raised the hand.
Thank you for the great talk. I would like to ask you about your almost perfect three-dimensional crystals of lattice crystal you discussed. You discussed mostly the local interaction, neighbor interaction, which results, for example, in the collective lamp shift, which is nothing else but polariton frequency shift for the waves propagating through this kind of medium. But what about observation of the boundary effect? Because this is 100 lattice length kind of crystal or waveguide or cavity, and then therefore you have to, it should be possible to see the resonances due to the eigenmodes of this waveguide or cavity. Do you have this in mind, or what did you see any manifestations of these eigenmodes of this system?
Actually, I think, well, thank you very much for your question. So I think what you're alluding to is the boundary effect, if I understood you correctly,
yes,
because
exactly.
it's a finite size system. And you're exactly right. When the photon, because these dipoles are interacting with each other, you can think of you use the word waveguide. This is exactly right, because you can actually think about you're engineering the dispersion of the photon as it propagates inside. And we can actually take an image, as I mentioned earlier, we can take an image of what's going on. The measurement I'm showing you here is the average across the entire cloud. But of course, you are correct. In the middle versus on the side, at the edge, the shift is different. This is a fact that we actually, in fact, next slide. This slide, I'm showing you actually directly taking the image of the dipolar shift on the right-hand side, left-hand side. You can change the dipole orientation. You can see the frequency shift changes side from the left to the right. And these are the effects we are observing but the edge effect that you described, it partly is blurred because we are averaging down by, it's a three-dimensional crystal. We are looking down with a microscope. And so there's averaging going on between, three-dimensional system turns into a two-dimensional map. And so some of the edge effects is blurred. And that's why I was telling you that the overall effect we're measuring is actually, when I quote a frequency shift, is an average of the entire cloud. But there is definitely spatial dependent information there. And this is the work that we're just starting. So some of these effects we will be exploring for sure. We have not yet looked at the photon dispersion properties and so on, as you are describing. But thank you.
Alexei, your question.
Okay, thank you for the talk. You said the words quantum gravity, but you said you're not doing quantum gravity. So my question is there a dream scenario where you can use your incredibly sensitive clocks to probe quantum gravity?
At the moment, Alexei, thank you for your question. At the moment, I don't see that. I think, at least it's exceedingly speculative. If you want to say, because of my atom is in coherent superposition, and because the gravity is quantized, and I can see those effects, that seems like another 20 order of magnitude away from our clock. So I can see linear gravity impact on coherent superposition, which I still consider that as very exciting. But I'm not yet. I don't see a scheme yet that we will be able to really probe the quantized gravitational field.
Okay, thank you.
Thank you.
Hans, your question.
Hi, Hans.
You need to unmute.
When we wait for Hans, I'm going to turn on my light really fast.
Okay, good. Hans, can you hear me? You need to unmute.
I'm sorry that Hans. But it's good to see him. It's good to see you, Hans.
Yes.
Yeah. So now,
okay, good.
Am I ready to ask the question?
Yes, please.
Yeah. Okay. Yeah, I enjoyed your talk very much. Opposite to what we have been doing on single ions and so on, you have many particles, and you mentioned the cooperative lamp shift, which you estimate or measure, maybe you can comment on this, to be in the order of 10 to the minus 19. So the lamp shift is a saturation effect. Yeah? And can you comment a little bit on this? Why do you call it cooperative and so on?
Thank you. Thank you, Hans, for asking that question. I know somebody would ask questions like that because the lamp shift is, of course, it's the foundation of the QED, and it's really referring to the fact of vacuum fluctuation for a single atom, right? And I think the cooperative lamp shift is something where people are talking about when two atoms are very close nearby, this atom will radiate in field, and this atom will feel the radiation from the neighboring atom as if this field is coming from another vacuum fluctuation. But of course, it's given by the atom. But in our system, of course, it's not just another atom. You have many other atoms nearby. And it's a collective effect of all these radiative fields adding on top of each other where this one atom in the middle will experience. And so from that perspective, the community has used this word cooperative lamp shift. Of course, it's not an original lamp shift. It's not a vacuum lamp shift. It's the describing how the radiation from one atom can be experienced by the another atom. And on top of that, it's a cooperative effect because all these atoms are adding up their field together. Does that make sense?
Actually, maybe you are aware of the work of Ralph Raxberger, who measured cooperative lamp shift.
Yes, exactly.
57 at 14 keV transition. Yeah.
I think one thing that's really distinguish this work a little bit is typically when people are trying to measure this, you put only one excitation in the system because it's a linear excitation. And this one is actually very much a many excitation regime because we put all the atoms in coherent superposition.
Yeah, I see.
And just maybe give credit to Misha Lukin. I don't want to give credit to him because he had a first-year graduate student, Derek Chen, and I met Misha in Moscow for the first time in 2004, and we just became friends. And we were talking about this, and Misha said, "I'm going to do this calculation," and it was his prediction. And along with Derek Chen, Derek is now a very successful professor in Barcelona, but it was their prediction that we finally. It took us 19 years to finally do it. Yeah. And this paper is actually just accepted in Science, so it's quite nice to see some of the predictions by theory takes a long time, but I'm very proud that the clock has got to this level of precision to be able to see those effects.
Yeah, it's amazing. Wanderley, you still have question or not yet?
Yeah, well,
yes, please.
Hey, hi, Joe. How are you? Very nice talk, and my question was more like Alexei on the quantum gravity stuff, because you're reaching a so high precision. Maybe somebody may think about an array of clocks that can really explore some quantum gravitational waves and things like this. Nobody's thinking about that.
Actually, Manley, definitely, I think your inspiration is definitely right. We are thinking about it. In fact, I rushed very, very fast in this particular slide that I was sharing with you. For example, here you have a gravity, right, towards ground, but I'm moving my atoms up and down. I can entangle all these atoms through this cavity. So now you are in a regime where the gravity is pulling on these different pancakes that have different redshifts. So you can really look at a very unique system where quantum entanglement and gravity are going to interplay. But in the end, though, if you think about it, this gravity is still linear gravity. It's not quantized at all. So from that perspective, that's why I was not sure whether quantum gravity itself will come into play.
But maybe an array of clocks may turn into possible detections that you cannot detect with a single clock only. Yeah.
So here, actually, Wanderley, that you can also think of each pancake as its independent clock. Yes. We actually we have this very high resolution imaging. We can see layers. For example, you can see layer by layer, and you can think of each layer as your clock, and that's your array of clock. If you have ideas, I will be very open. Absolutely, because I feel this is probably one of the most exciting frontier, right? To connect quantum physics and gravity. If we can do that, that would be amazing. And I think even just my maybe humble opinion, even just connecting linear gravity and quantum physics, it's still quite interesting to me.
No doubt about it. But I will contact you. I may have some suggestion.
Thank you.
Thank you for the talk.
Of course.
So we have only 10 minutes, less than 10 minutes before the next session. So let's thank once again June and Peter for really fantastic talks, which caused so much excitement. Thank you.
Thank you, Olga.
Thank you.